This is Lab 7, magnetic fields. This is part 2 of the Helmholtz coil method of determining the value of the magnetic charge. This here is the setup for this activity. We have a power supply, Pascal power supply, a variable resistor. We've used this in the past as when we created a voltage divider. We have our magnetic balance. We have an item called a Helmholtz coil. And we have a ammeter to record the current in this circuit. This Helmholtz coil is this device here, and it's created by having two sets of loops of wire that are separated by the radius of the coil itself. So find this radius and it should be the same as this distance here. You need to know what this radius is, and you need to know the number of loops in one set of the coils. You can take a micrometer and once you turn it on, and if you have to, you can zero it. But you'll take and use these inner jaws on the inside of it to determine what the diameter is, or you can use the outer jaws here and snuggle it up to the outside of the coil, the cylinder, and get its diameter. And in fact, you can, once you get both of these, you can take the average and let that be, well, it's probably the outer diameter that you'll want to use. Let's go ahead and use the outer diameter, and then take half of that for the radius. So you'll have the radius of this coil and the number of loops in it. Okay. So once we have a current flowing through these wires here, through the loop coils and the Helmholtz coil, you're going to be creating a magnetic field. It'll be pushing downward, pushing this arm down to oppose the gravitational torque on this side. So once again, you want to take and achieve a zero setting here, a neutral setting for the balance, whereupon you'll know that this magnetic torque is equal to the gravitational torque. And once again, we'll take and solve for the magnetic torque by using this equation. So you'll know these numbers here, and you'll need to calculate what the magnetic field is in the coil, and that's given by this equation. U sub O is a constant. Okay, it's 4 pi times 10 to the minus 7th, and it has units of Tesla meters per amp. Okay, N is the number of loops in one set of Tesla coils. I is the current in amps. A here is little r, the radius of the Tesla coil. Express that in meters. Okay, so that your units come out right. So we've got a situation that looks like this, and you've got current flowing in here, and by the right-hand rule, as you look at the way the current flows in, and you can see the wires set up, by the right-hand rule, you can see that this magnetic field is pointed downward. Okay, let your fingers follow the curve of the wire that it's running through, and then as you close your fist, your thumb sticks out in the direction of the magnetic field direction. Okay, so once again, you're going to take and use a mass rider along all those notches on the right-hand side of the magnetic balance, and you're going to oppose them with enough current, okay, so that you've got this balance in the neutral position. So you're going to record all these different I's, whereupon you will take and calculate the corresponding B values. Calculate the I's, or record the I's, calculate these B's. Okay, and you're going to plot the magnetic force as you computed earlier along against the magnetic field strength. You should get a fairly straight line, the slope of which will be equal to P, the magnetic charge. Once you finish that, you can take and compare that value to the value you got in part 1. They should be similar, should be very similar. I would suggest that you use these sticker cables, not the thin ones with the alligator tips on the, do not use these. Use these sticker cables for this experiment. Now I've got this hooked up already, so you can see how from I've got current flowing from the power supply to the variable resistor. Okay, it's connected here and then connected here. And this can slide back and forth as a fine control of the current. Then from here, it goes into the Helmholtz coil and then comes out here on this side and goes to the ammeter. This post here says positive. It should be towards the positive pole of the power supply. And then on the other side, I've got a wire that's connected up to the negative pole of the power supply. Okay, we're using DC power here. And this here is a DC ammeter. So I've got a mass rider. I'll place it on one of these. Oops, place it right there. And if I turn this on, you can see that there's current flowing, and let me see if you can actually see the meter here. Well, maybe not so easily. But you can see the needle somewhat. The lighting's not the best. But you can adjust this back and forth until you try to get it balanced. And then, like I said, you can make slight adjustments with this. Fine adjustments. And continue to do this until you get it balanced. And once again, if this thing's going to oscillate back and forth, and if it moves one tick mark to the left and one tick mark to the right, you might consider it, you know, in a neutral position. So once you achieve this neutral position, take and record this value of current. Now these meters, let me hold one up here. Okay, they have a couple of different scales to them, and they have different inputs. Like I said, there's one marked positive, like this one here, it goes to the positive pole, and the other, and you have your choice from the others going to the negative pole, and those choices tell you which scale you're going to be reading on. So once you do all this, create all this data, you should get a nice straight line, okay? And it's the slope of this line here that we said is equal to P. And that should agree with the value you achieved in part 1. Let me add that as you continue in this experiment here, the power supply will be heating up this variable resistor. This will get warm. Okay, I don't think it'll get warm enough to hurt you, but it'll actually feel hot at some point, or can.